2000 in the first decade of this century. So let me start with the example. If you look at this graph or the plot, you will remember what we were discussing the last time. The similar plot, we have Q on the y-axis, quality factor on the y-axis, and noise factor on the x-axis, and we see that for different quality factors, different values of quality factor, the noise and dip occurs. So in our previous discussion, what we did is we choose Q to be 1.4, arbitrarily choose the gate source voltage to be 1 volt, and the design ultimately gave us a noise factor of 1.12 and a noise figure of 0.49 dB. And this required the gate source capacitance to be 631 femtofarad, and then undegenerated inductance that to be 0.17 nanohenry, and gate inductance to be 12.2 nanohenry, and W or width to be 392 micrometer. I bias is equal to 69 microampere. So bias current is 69 microampere. So this is what we saw in the last time. Now also we saw this when the bias point is at for gate source voltage is 1 volt. When we determine the bias point with gate source voltage is equal to 1 volt. So if you look at the 1 volt line, dashed line is the 1 volt line. To its left we have low power amplifier LNA. To its right, if you are operating beyond that, then the high power line amplifier. So current density will above 200 or 180, those current densities, they will give us high power performance. Below 180, they will give us low power performance. This we have seen in the last class. Now, in the design, what we have to do is we have to handle the low power dissipation. What is low power dissipation? As you know, the device has some resistivity. Besides that, there are resistors associated with it. So the power will be lost when you have resistive component. Power will be lost as heat in the resistor. So that loss is called dissipation, power dissipation. So if you are using low power and power is dissipated, some amount of power is dissipated, so useful power is very small. So that is what we have to handle. So the dissipation should be small at low power. So the formula that we want to use here to handle this low power dissipation is the bias current. The expression for bias current is the current density IDEN into W. That is the expression for bias current. And the expression for F and noise factor is 1 plus omega 0 by omega t into gamma into GDO by GM into 1 upon 2Q whole into 1 minus 2 absolute C xi d plus 4Q square plus 1 that into xi d square. Now if you have, once you look at this, then if we use lower current densities, that is IDN is small, then we will get the benefit of low power. But the negative part is if we are using low current density, then IIP is lower, so lower FT. Now look at the other one, W. W, if it is lower, then the benefit is lower power. That is there, that benefit will work. But negative points are on lower gate source capacitance, because gate source capacitance is equal to 2 by 3 into W into L into COX. So if lower gate source capacitance, that will raise the quality factor. So higher Q, because Q is equal to 1 upon omega 0 CGS into 2 on RG. So that is one negative point. So high Q. Second is higher F. F becomes high if we have W is low. For low W, F is high. So these are the two disadvantages of lower W. So the first step in redesigning the LNA is look for low current density. So high density should be lower. That is the first step. So go to a new bias point. Instead of the bias point voltage between gate source voltage was 1 volt. Instead of 1 volt, go to 0.8 volts. So slightly less VGS. So VGS is less. So once VGS is less, we'll have a lower current density. So our current density will be low. Now we have to verify if IIP3 is still okay. Or to know that, we have to know what is the Q. So we are going to recalculate the whole process parameters, all parameters we are going to recalculate. High density is equal to 100 microampere per micrometer. Assume that only change is GM upon GDO and FT. These are the only change. Now GM upon GDO is equal to approximately equal to 0.78 by 1.15. So that is approximately equal to 0.68. So GM by GDO is 0.68. If you use this value GM by GDO of 0.68, then XID, which is GM by GDO root over of delta by 5 gamma, that will be equal to 0.63 into root over of 2 by 5, that is approximately 0.43. So XID is 0.43. Then omega T is GM by CGS, or the transconductance by transconductance divided by gate source capacitance. So that will be equal to 0.78 divided by 2.9. Transconductance is 0.78 and capacitance, gate source capacitance is 2.9. So put those values, that will give you 2 pi into 42.8 gigahertz. So omega T is equal to 2 pi into 42.8 gigahertz. So these come from the previous graph, the graph that we saw. Now we have to replace the noise factor scaling coefficient. Also you have to plot it over a wide range of Q. The noise factor scaling coefficient is to be plotted over a wide range of Q. We know the noise factor F is equal to 1 plus omega 0 by omega T into gamma into ZDO by GM into 1 by 2 Q whole into 1 minus 2 absolute C is ID plus 4Q square plus 1 that into Jd square. So this last part is the noise factor or noise factor scaling coefficient. That we have to draw a plot between this expression and Q. The noise factor scaling coefficient versus Q for 0.18 micron NMOS device. Look at this device. Here again you can see as Q increases to large value around 2, these plots for different C they merge. But when Q is small, at around 1, Q is equal to 1 or below, there is small difference between them that you can see. So as you keep on increasing the Q value, they start merging, but initially they are small. Now there is small difference. Although there is small difference, each curve has a dip. Each curve is showing a dip. Okay. Now remember this second step in the design is we have to lower the W or raise the Q. How much we will raise the Q or how much we will lower the W. First is the capacitance, gate source capacitance, that is 2/3 WL COX. Q is equal to 1 upon omega 0 CGS into 2RS. I bias, this can be related to Q as I bias is equal to I density into W. That you can write as I density into 3/2 LCOX into CGS, because CGS is equal to 2/3 WLCOX. So that you can also write as I density into 3/2 LCOX into, for CGS you can write 1 by omega 0 2RS into Q. So looking at this expression for I bias, we can say I bias is proportional to 1 by Q. So we have already chosen Q to be 1.4 earlier. Now let us choose Q to be 6. So if we choose Q to be 6, this choice of Q of 6, this alone will cut power dissipation by more than a factor of 4. Combined with the lower I density, almost a factor of 8 reduction in power is required. So new value of W will be W is equal to 392 micron into 1.4 by 6. So that will give us approximately 91 micrometer. So W should be approximately 91 micrometer. Now power dissipation. What will the power dissipation? Power dissipation we will find out once we find out I bias. I bias is equal to I density into W. I density is 100 microampere per micrometer. W is equal to 91 micrometer. So multiply them, that gives you 9.1 microampere. At 1.8 volt supply, if you give a 1.8 volt supply, which is standard supply, so then power is equal to I bias into the supply. So I bias is 9.1 microampere into supply is 1.48 volt. That will give us 16.4 microwatt. Now noise figure, FT we have previously calculated. Get the scaling coefficient from the plot that we have seen. Look at the plot and get the scaling coefficient for the FT. Omega 0 by omega t will be equal to 2 pi into 1.8 exponential or 1.8 into 10 to the power 9 divided by omega t is 2 pi into 42.8 into 10 to the power 9. So that is approximately 1 by 23.8. Scaling coefficient is approximately 10, and that you can see from the previous figure. Noise factor will be 1 plus 1 by 2.8 into scaling coefficient, which is 10. So that will be approximately 1.42. And so that will be noise factor. Noise figure will be 10 log into noise figure, that will be 1.52 dB. Now updated component values will be assume RS to be 50 ohm, Q is equal to 6 that we have taken, F0 is equal to 1.8 GHz, Ft is equal to 42.8 GHz. Then capacitance, gate source capacitance is from Q is equal to 1 upon 2 RS omega 0 CGS. From that you will find out CGS is equal to 1 upon 2 RS omega 0 Q. We know what is RS, we know what is omega 0, we know what is Q. Put those values, CGS is equal to 147 femtofarad. And LDEG, that we will get from this formula, Gm by CGS LDEG is equal to RS, from which LDEG is equal to RS by omega t. Put these two values, LDEG is equal to 0.19 nanohenry. Then LG calculation is from this formula, 1 upon root over of LG plus LDEG into CGS is equal to omega 0. Now put the value of omega 0, LDEG, CGS. Then you find out LG, that will be equal to 1 upon omega 0 square into CGS minus LDEG. Put these values, omega 0, CGS and LDEG value. Then LG will be equal to 53 nanohenry. So we have found out the component values. Now the amplifier is to be connected to a load, because the power from the amplifier must go to a load. So on the load, the amplifier termination is on a load. So we have to include the load. Here for the load we will use a resonant tank circuit. So that will be the load. So if we take that to be the load, then what we will do is we will add the load to achieve our voltage gain. Whatever voltage gain we require, that we will achieve using the load. Remember that in practice we use a cascode device, but here we are using a tuned circuit, resonant tank circuit, as equivalent to the cascode device. What we are doing here is we are neglecting the gate drain capacitance. That will be neglected in this analysis. Now look at the figure given below. I hope you remember the figure. There is a dashed line. To the left of the dashed line is the source. Towards the right of the dashed line is the device of the amplifier and the load. Its equivalent is shown in the top. Exact circuit is shown in the bottom. In the top, the equivalent is for the load. We have added the load noise with R and L, and then the total voltage we have taken as V in. Then for the device we have used the equivalent circuit, which is a voltage controlled current source. That is the equivalent circuit. Otherwise, and the noise due to the device, which is INDG. That is the noise due to the device. That is joint. And for the load, from the load there is the output current and there is noise current. Noise output and current output, both are there. So red one is noise and black is the current. Now let us calculate the gain. So assume that the tank circuit is resonating at the frequency omega 0. Assume Zin is equal to Rs. So for matching Zin is equal to Rs, that we will assume. Then VGS, voltage between gate and source, is equal to V in by 2 Rs into 1 by J omega 0 CGS. This comes from your simple circuit analysis. So that gives you Q divided by J into V in. Take V in common, rest of the thing if you consider, that is Q by J. Take V in by J common, rest of the thing is J Q. So therefore VGS is equal to Q by J V in. I output current is equal to Gm into VGS into Vin. So I out is equal to Gm into Q by J into V. So that gives us V out is equal to minus Gm into RL into Q by J into V. So this way again. Now how to set the gain? So setting up the gain is equal to Gm into RL into Q. So the parameters are Gm and Q. These are to be set by noise figure and IIP3 considerations. Note that Q is of input matching network, not the amplifier circuit. It is of the Q of the input matching network, not amplifier load. RL is the free parameter. Use it to set the desired gain. So by we don't have any control over Q, we don't have any control over Gm, which is transconductance. So our control is over RL, that is the free parameter. Use it to set to the desired gain. Once you know what is Q, what is Gm, then just control RL. So note that the higher the RL for a given resonant circuit, the capacitive load will increase the QL, that is Q of the amplifier load will automatically increase. So there has to be a trade-off between amplifier bandwidth and gain. Generally, we set RL according to overall receiver noise and IIP3 requirements. Our higher gain is better for noise, that we know. So very large gain or very high QL is generally avoided to minimize sensitivity to process or temperature variation, which will shift the center frequency or omega 0 to avoid parasitic oscillations. We don't require parasitic oscillations, we require the tank circuit to oscillate only. Now, the moment we said parasitic oscillations, we have to know from where we get the parasitics. The parasitics usually come from packaging. Once you design the amplifier, then you have to fabricate it and package it. From the packaging, there is a chance of getting the parasitics. So this shows you, the figure shows you what happens, actually what happens. So equivalent source is shown on the left side. Right side shows you the device and the circuit. If you look at this, we have an external inductor, then we have an inductor because of the bond wires. So that is connected to the device and source. Between the device and source, the inductor due to the bonding. Similarly, there is an inductor due to bonding between the device source and the ground, so which is L bond wire 1. Similarly, L bond wire 2 is the inductor due to the bonding wire between the source, the DC source and the device, or the output load and the device. So that gives you a noise voltage, then you know what is the noise current source. And now you have mixture and other circuits will be connected to the output, and there will be noise current which is going through the source. So bond wire means in the package, the wires or the traces that are used for to connect different points. These are called bond wires. So bond wire inductance, they cause two issues. Value of degeneration inductor is altered because of these additional inductances due to bond wires. Noise from other circuits coupled to low noise amplifier. Now how to handle these issues? To handle these issues, as we already know, what we do is we go for differential connection. So this now we will consider a differential low noise amplifier. Differential NNA. Look at the circuit. This is a standard differential circuit. Advantage is value of LDEG is now under control. You can have much better control of LDEG, much less sensitivity to noise from other circuits because of the differential connection. Disadvantage is you require, because two devices are there, so twice the power as a single-ended version and requires differential input at the chip. These are the disadvantages, inherent disadvantages. Now, note that you should be generous with substrate contact placement when you are designing the device. When you are designing the device, you must be generous with substrate contact placement. Because if you do that, then having an abundance or enough number of nearby substrate contacts helps in three ways. First is it reduces possibility of latch-up issues. Second, it lowers the earth substrate, means the substrate resistance because of abundant electrons, available electrons. So it reduces or lowers the substrate resistance and its associated noise. Once resistance is reduced, noise will be reduced. Then it impacts the LNA through backgate effect, GMB. There will be a GMB or conductance backgate conductance will be there. So which will absorb the stray electrons from other circuits that will otherwise, if these are not absorbed, then the stray electrons are going to inject noise into LNA. Now what is the negative or the disadvantage of this? This takes a bit extra area because you are using more substrate, you are generous with substrate contact placement, so you require more area. So it will use little bit more area. Otherwise it has advantage. Now let us consider the broadband low noise amplifier design. Most of the broadband systems, they are not very stringent on their design. So most of broadband systems are not stringent on their noise requirements, as in the case of wireless devices or wireless. Equivalent input voltage is often specified rather than the noise figure. So that is important. Important factor is input voltage, equivalent input voltage rather than the noise figure. Typically, it uses a resistor to achieve a broadband match to the input source. Look at the figure which is given below. What we do is here, a high-speed broadband signal comes to a package interface using through the PCB trace, and package interface is connected to LNA with the input impedance Z. So we know from earlier that this will limit the noise figure to be higher than 3 dB. So noise figure will be more than 3 dB. For those cases where low noise figure is important, are there alternative ways to achieve broadband match? That you have to think. We have discussed different methods earlier of doing this. So that is what we have to think. For example, remember that noise factor calculation for resistor load. Remember, I try to remember that what we were doing there. In that case, we had the source and we had the load. So RS and RL, look at the left side figure. RS and RL, RL is the load, RS is the source resistance. That is equivalent to source resistance followed by a noise source, then the load resistance preceded by a noise source. So based on that, total output noise expression is this V output square or variance covariance of V noise output, total noise output is RL by RS plus RL square into covariance of noise source noise plus RS by RS plus L square into covariance of RL noise. Total output noise due to the source is covariance of input voltage is equal to RL by RS plus RL square into covariance of noise due to source. Noise factor F expression is 1 plus RS by RL. Noise figure for the amplifier with a feedback resistor. If you look at the amplifier here on the left hand side, there is a feedback resistor RF. So in that case, what will be the noise figure? Its equivalent circuit considering the noise is you add a noise source for the RS, add a noise source for the RF. That much you have to do. With that, the total output noise, assuming the gain is to be large and noiseless gain, then the covariance of output noise, total output noise is equal to approximately equal to minus RF by RS whole square into covariance of noise source plus covariance of feedback noise. Total output noise due to source, assuming A to be large, is covariance of input voltage is equal to minus RF by RS whole square into covariance of noise input noise. Then noise factor, as in the previous case, will be equal to 1 plus RS by RF. Input impedance for the amplifier with resistor in the feedback. Now Zin will be equal to ZA by 1 minus gain, that is equal to RF by 1 plus A. That comes from the op-amp circuit. If you choose Zin to match RS, so if Zin is equal to RS, then RF is equal to 1 plus A into Zin, that is equal to 1 plus A into RS. Therefore, noise figure now will be lowered by being able to choose a large value of RF, because F is equal to 1 plus RS by RF. By choosing large value of RF, you can lower the F. Now, resistive termination versus resistor in feedback, which is better? Let us consider this two. So resistive termination, first one is resistive termination. Look at the resistive termination. For termination, RS is equal to RL, F is equal to 1 plus RS by RL, which will be equal to 2 because RS is equal to RL. For the feedback, resistor in feedback, when we consider the termination, RF is equal to feedback, RF is equal to 1 plus A into Zin, which is equal to 1 plus A into RS. F is equal to 1 plus RS by RS, which is equal to 1 plus 1 by 1 plus A. So if A is large, then F is small. If you look at this, the larger the A, the smaller the F. When A is equal to 0, there is no absolute A is not working there, then there is F is equal to 1 or F is equal to 2. Otherwise, F will be less than 2. F will always be less than 2 in the second case. Now, consider an example, series shunt amplifier example. This was this circuit. This was examined earlier. We have examined this circuit earlier. For this circuit, you can find out what is RIN, what is ROUT, input resistance and output resistance. Just find the equivalent circuit of the circuit and find out the input resistance and output resistance of the circuit. What you can do is look at the book. The book points out that this amplifier topology or this amplifier configuration is actually used in noise figure measurement systems like HP 8970A. HP now, Hewlett Packard is no more. Agilent is also no more. Now there is a new thing has come up. So that gives you, it is likely to be a much higher performance transistor than the CMOS device. Recent CMOS LNA techniques is now consider increasing the transconductance for a given current by using both PMOS and NMOS devices. So that is a recent technique. Key idea is reuse the current here. So to know more about this, look at this paper by Karanicolas. Look at this paper which came out way back in 1996. Have a look at this paper. That gives you an example. Similarly, biasing also you can see here the same thing. PMOS is biased using a current mirror. You can see here the lower part is the mirror part, current mirror. So PMOS is biased using a current mirror. NMOS current is adjusted to match the PMOS current. Another approach, forget this. This is not required. And now, can we create broadband matching network using LC ladder filter? LC ladder means you have a LC and then you have another LC, then you have another LC, and these are connected like a ladder. So that is what is LC ladder filter, a ladder filter design technique. The figure here shows you, gives an example of a CMOS example of broadband LNA design approach. Look at this figure to understand what has happened in this case also. Look at this reference by Bevilacqua. This is another paper. Instead of using CMOS or FET, we are using bipolar here. This was by Ismail and his group. This is another paper in which GM is boosted. The CG amplifier. GM means transconductance is boosted. The CG amplification. So noise figure improvement occurs here. F is equal to 1 plus gamma by alpha, as you know, and F is equal to, once you boost it using an amplifier, then F will be 1 plus gamma by alpha into, because of amplification, you will get 1 by 1 plus A because of the feedback in the feedback amplifier. So, but here the amplifier adds noise and power. Look at this paper also. Then the problem in the previous one is because of the presence of transistor, there will be loss, power loss. Can you avoid that? So what we do is, instead of using a transistor to boost the power, we are using a transformer, step-up transformer. So just remove the transistor there, the booster there. Instead of the active booster, use a step-up transformer here. So here we use a step-up transformer which increases GM. So transconductance is increased by a step-up transformer. And if you do that, then F is equal to 1 plus gamma by A. Then because of step-up transformer, it will be now, instead of 1 by 1 plus A, it will be 1 by 1 plus Nk. K being the coupling coefficient, N being the number of turns in the transformer coil. So the transformer provides gate and source with voltages 180 degree out of phase. So this effectively increases the voltage between gate and source. Then on neutralization, revisit the neutralization. It uses the neutralization process this circuit we have already seen in the last class. So in this, its uses are neutralization uses are power consumption will be output swing, power consumption will be controlled. So one of the use is power consumption, then output swing is under control. So additional drop for the tail current will occur there. There is differential output, as you can see from the circuit diagram. M1 and F2 are in differential mode. Then there will be matching between CGD and CN. This is because of the neutralization. And then the next question is, instead of doing that, can you tune out the CGD? Instead of using CGD, can we tune out the CGD instead? Conceptually, you can do that by a series inductance L. So CBIG is necessary to block the DC between input and output. That too you cannot avoid. So that will be there. Inductor value is too large, so inductor size will be very large. Both plate and parasitic capacitance of BIG will be also coming into picture. But this is not advisable. This circuit was proposed by Kashan. Kashan and his group. You can see his paper. The paper is given here. And then neutralization by transformer feedback. Instead of using that, now you can go to use a transformer as the feedback in the circuit. You can see the circuit transformer feedback circuit. Neutralization of CGD by CGS. If N by K is equal to CGS by CGD, that will neutralize it. Advantage is there is no DC drop because you are using only inductors, so there is no DC drop. This can operate at low supply voltage. Power match by inductor degeneration. Then no additional power consumption is there. CGD to CGS matching is better than CGD to CN matching. So neutralization is done. The same thing can be implemented in a differential form. You can see the figure here, and download the material. You will get the figure. Just only see that the two devices Q1 and Q2 are connected in differential mode. Differential output of LNA. Again, you can see that this circuit. This provides differential output to drive the balanced mixture. Now look at the paper, technical paper that is given at the below bottom. Then adjustable gain. You want to adjust the gain, increase the number of devices. Depending on the number of devices, the gain of the amplifier will be adjusted. So gain is adjusted by diverting output current in the cascode stage. So use a cascode device. So with that, we come to the end of the discussion now. We'll take a break and come back after the lunch at 2:30.